All right, class, welcome back. Here we are, lecture 12, continuing in our discussion of time-dependent response theory, having last lecture worked out the so-called fluctuation dissipation theorem, which is worth restating. It says that if I took a system at equilibrium and applied a time-dependent force to it, such that I have some initial reference Hamiltonian H naught, I add to it some f of t, multiplying some variable in my phase space A, that the way in which the system would relax spontaneously generated perturbations to A, namely the correlations in time associated with A, as measured through its time correlation function, like so, determine exactly how that system would respond when that force is turned on. So we have a response function chi, which is now time dependent, that is exactly given by the time correlations, the way in which A spontaneously fluctuates or relaxes from fluctuations in time. And the constants of proportionality are a minus and a beta, much like we saw in spatial linear response theory. There's a differential and a Heaviside function which is there to invoke causality. This response function enters in through a relationship that tells me how A changes in time from some initial equilibrium A is given by an integral over all times up to t, that response function, and then the perturbation that we're applying. So this is a pretty powerful piece of insight. It extends our notion of linear response away from just static thermodynamic questions to actually those of time dependence, how a system relaxes subsequent to a perturbation. So we're going to do two things today. First, we're going to generalize these results away from the classical limit in which we've derived them thus far and generalize them to a quantum mechanical system in which there are some additional technical difficulties, which will require us first to have a brief discussion about quantum time correlation functions. And having done that, we'll write down the fluctuation dissipation theorem for a quantum system. And then we'll start talking about some applications of time-dependent response theory, and specifically work out a theory of linear absorption for a classical system. This will be something you will generalize in your homework to the quantum case of an actual spectroscopy measurement and a linear absorption in a vibrational chromophore. Okay, so that all being said, let's go ahead and get started. So our aim initially is to extend our result to the quantum realm. And to do so, we first need to talk about quantum time correlation functions. Okay, so time dependence in quantum mechanics results or is predicted by the time-dependent Schrodinger equation if I have some wave function psi up to a factor of I h bar, its change in time is given by the action of its Hamiltonian on that wave function, time-dependent Schrodinger equation. Cool kids call TDSE. This is an equation which can be formally integrated. Yielding the time dependence of psi, some wave function, is where it started, some initial condition, and a complex exponential, a phase factor, generated from the application of the Hamiltonian on that initial wave function. This already is kind of there's already interesting observations one can make associated with the time dependence quantum mechanically, namely that the norm of the wave function is unchanged. Its time dependence results entirely from a phase, how it rotates within some Hilbert space. It's worth noting, because this will come up later in the lecture, that if I was to define some imaginary time, IT, as beta h bar, a quantity we have seen come up before, then the time-dependent Schrodinger equation in imaginary time, sorry, this is now beta, takes that form, which has a formal integral which generates that Boltzmann factor. So indeed, just like the Liouville equation, which generates the time dependence in a classical system, the time-dependent Schrodinger equation generates the time dependence in a quantum mechanical system. There are important differences being that in the Liouville equation, we were working directly with probabilities. Here in the Schrodinger equation, we're working with probability amplitudes. But in moving from real time to imaginary time, we find that the Boltzmann distribution pops back out. If we took an expectation value, I would get the Boltzmann operator back out. So this is another reflection of the ability to rotate along some time axis from the real time to imaginary time and make contact between dynamics quantum mechanically and thermal statistics quantum mechanically. So solving the Schrodinger equation, the time-dependent Schrodinger equation, given this phase factor, is then akin to solving the time-independent Schrodinger equation. If we can determine those phases and the projection of some arbitrary wave function onto the eigenstates, then we can predict the phase factors. So specifically, the time-independent Schrodinger equation, H acting on some eigenvalue, eigenfunction, psi k, can be solved with eigenvalues ek. If we have those eigenvalues and eigenvectors, we now can predict the time development of the wave function, and therefore any expectation value over those wave functions. So specifically, consider some thermally averaged operator A. Its time dependence can be written down first by noting a way to write down the thermal average is to sum overall states, here indexed by the eigenstate of the system, the probability associated with that eigenstate, and the expectation value, quantum expectation value of the operator A. In that time-dependent eigenstate. Where P of K, if this is a thermal distribution, satisfies a Boltzmann distribution, just like in a classical system, with normalization constant given by some partition function. So a time-dependent average, quantum mechanically, looks very similar to a classical average, with the exception that in addition to summing over the probabilities of an eigenstate, I have to project that operator into the eigenstates through that basis transformation. A consequence of this structure is that I can pull out the time dependence from the wave function, from the state of the system, and put it into the operator itself, much in the way we did this with the Liouville equation. I can think about a Schrodinger picture in which the states of the system change in time while the operators are time independent, or a Heisenberg representation in which the states are stationary and it's the operator that changes in time. So this is the Schrodinger picture. A Heisenberg picture would be to say that average of A of t is equal to that weighted sum again. But I can pull out the time dependence of that state using the solution to the time dependent Schrodinger equation. It is a phase, a Braun-Ket are related through complex conjugation. So rather than a minus sign, I have a plus sign here. I have A in the middle. I have the complex conjugate of that unitary evolution operator, and then acting on a stationary state of the system. Noting that P of K is Boltzmann distributed, I could, if I wanted to, actually pull it inside leaving me with one big quantum expectation value, where in addition to the unitary operators moving the operator A in time, I will have a Boltzmann operator whose action on psi gives me the eigenvalue. Wherein defining P of K, I now have to also introduce, which I could do in a symmetric sort of way, the partition function as the trace of the Boltzmann operator, as we saw before. And now I can note that both numerator and denominator are sums over expectation values, which thus are traces. And if I define this quantity here as a operator of T, I can now write down that the thermal expectation value of A is given by a trace of a Boltzmann operator, and this now Heisenberg operator, which has explicit time dependence, normalized through the trace of the Boltzmann operator. So this is how we go in between a Schrodinger and Heisenberg representation, associating time dependence either with the states, as we did initially here, or through the operators by pulling out that unitary evolution operator and associating it with with A. So note the symmetry here. Now, just like we had classically, an expectation value is a sum or an integral in phase space over all possible states, weighted by a Boltzmann factor. In this case, that factor is an operator, and the thing that we're averaging, the operator A. You should be able to show simply that, just like classically, in an equilibrium distribution, that quantum thermal expectation value is stationary, that it does not itself depend on time, that the origin of time is not special. So just as in the classical case, time dependence is encoded not in single time averages, but in correlation functions. So consider now the quantum time correlation function of some operator A at time t and B at time t prime. So thermally averaged. We can express that quantum time correlation function in the same way we just did that single time function, through a sum over the eigenstates weighted by their Boltzmann probability, with an expectation of, now in the Heisenberg representation, time-dependent operators, like so. I can insert a resolution of the identity here, noting that the full set of eigenstates is complete. So I can insert a 1 by inserting a sum over the set of states, an outer product of those states. I will get a new index, say K and M, P of K, first expectation value. Let's be consistent and associate time with A. That outer product went here, so now I have like so. If I actually opened up those time evolution operators, remembering that this is nothing but e to the I h t over h bar operator A time independent e to the minus I h t over h bar, psi of k and psi of m are eigenvalues of that Hamiltonian, so I know what the action of H is on them. That just returns the eigenvalue E of k or E of m. Doing that for both A and T, I can now write the time correlation function as a double sum, weighted by a Boltzmann probability. The matrix element A, K, M, B, M, K, and two product of phase factors, e to the minus I, E, M less E, K times T minus T prime over H bar, where that is the expectation value of B, like so. So note this. Note first that the quantum expectation value is simply computable if we know the solution to the time-dependent Schrodinger equation or the time-independent Schrodinger equation. That the time correlation function is just a product of expectation values, quantum expectation values, matrix elements in the energy eigenstate basis, and a phase factor, a complex exponential that says that those correlation functions will oscillate in time. So that is something very distinct from the classical case, in that a quantum time correlation function, unlike a classical time correlation function, has both real and imaginary components. That actually means that quantum time correlation functions are not directly measurable. We can't measure imaginary numbers. Their individual real and imaginary parts, however, can be deduced from measurement. The fact that A and B are also operators means that their positions in that expectation value are important. A and B might not necessarily commute. And so if we have to be a little bit careful about ordering, noting the relationship between the time correlation function and those complex exponentials, if I would have put B instead of A first, as I unwrap that quantum time correlation function, I would be complex conjugating or transposing the matrix elements and that complex exponential. So one can actually understand the role of the non-commutivity of those operators by taking a quantum time correlation function and noting that its complex conjugate, denoted here with a star, is equal to simultaneously swapping their positions and flipping time. And from stationarity, that means that it's just swapping their positions. So because a quantum time correlation function is real and imaginary, it can be complex conjugated. That acts to swap the positions, the relative ordering of A and B. And through stationarity, that's all it does. Okay, so those are some properties of quantum time correlation functions. One has to be careful about their orderings, but provided a set of energy eigenvalues and their associated eigenfunctions, one can compute them straightforwardly through that equation above. Okay, so now we're in a position to actually talk about the linear response of quantum systems, working through what is known as the quantum regression hypothesis. Reflecting the nomenclature we invoked last lecture in Onsager's regression hypothesis, the idea that the way a system relaxes from a perturbation is the same way it relaxes from a similar spontaneous fluctuation. So let's try to follow the same procedure we did previously. Let's imagine taking a system defined with a Hamiltonian operator, H, which is decomposable into a reference piece, and now some time-dependent force that acts linearly on the operator, A. And as before, linear response, the form, the response function, should be independent of the specific form of the perturbation. So let's take a simple perturbation, f of t, which is piecewise constant going between f bar for all times in the past before the origin t equals 0, and is turned off at 0 and left off for all times. If we wanted to understand how the average of A of t evolves in those times after the perturbation is made, so after f is turned off, I could express that time-dependent average through a sum over the eigenstates of H, full H, psi of k, a Boltzmann operator, because that's going to be the initial condition set up by full H. The time development, however, is under only H naught. And that probability is initially normalized by computing that partition function. So again, at time 0, I am starting from an initial set of states determined by the action of the full Hamiltonian. But subsequent to turning the force off, the evolution of A is under a Hamiltonian just H naught. Now note something about these things. So first, let's actually just for completeness, Note specifically that these states are indeed the eigenstates of the full Hamiltonian with their associated eigenvalues. Now note, if H naught and A commute, then I can pass H naught through A, H naught and H naught, of course, commute with each other. They can then sum in the argument of that exponential, leaving no function of time in that right-hand side of the equation. And thus, if H naught and A commute, A will not change. It will be a constant of motion. There will be no relaxation. It is a conserved quantity under H naught. However, so that's like saying if A was itself H naught, the energy is conserved, so it does not change. However, in most cases, H naught and A will not commute, in which case there will be some time dependence. But we still have a problem in sorting out that time dependence because we have operators in those exponentials, so we can't use the same tricks we used before. Specifically, we made judicious choice of a Taylor expansion of the Hamiltonian. So previously, we took the Boltzmann factor, said that was equal to this reference piece times the perturbation, and then Taylor expanded that perturbation to first order to then work out the linear response of the system, assuming F is small. This step does not work quantum mechanically. If A and H naught do not commute, then that first line is not valid. So we have to figure out another trick to understand the functional dependence of the Boltzmann operator on F when F is small. All right, that's a bummer. That requires some technical tricks. So the way to solve this problem is to introduce something called the resolvent. Specifically, I can take that Boltzmann operator and Laplace transform it and define a quantity G tilde of S in doing so, which will be equal to, through the definition of a Laplace transform, an integral over that function where the constant that I'm going to integrate over is beta. And I introduce a Laplace variable S conjugate to that beta. Now that's an integral I can do, both the Boltzmann factor and the kernel and the Laplace transform are exponentials. So that gives me 1 over S plus, unwrapping the Hamiltonian, H naught less constant F times A. Now, H naught and A are operators, but I can rewrite through a partial fraction decomposition, that fraction is 1 over S plus H naught times 1 over 1 minus F bar A times 1 over S plus H naught. I can factor out the quantity or the operator 1 over S plus H naught. And now this is a quantity that we can Taylor expand for small f. Specifically, if f is small, this resolvent will take a form what the resolvent would have been in the absence of the perturbation. So if f is 0, let's call this g naught tilde of s. The 0th order term is just g0. Now, the first order correction multiplies that g0 of s. 1 over 1 minus a small number is 1 plus that small number. The 1 is the 0th order term. The small number is f bar a operator, and then the resolvent again in the absence of the perturbation. And then that is an expansion good up to f bar squared. Now I could take the inverse Laplace transform g of s, which was the Laplace transform of the Boltzmann operator, remember? And what will I find? I will find that the Boltzmann operator is approximately given by the Boltzmann operator in the absence of the perturbation, g naught. And the first order term now has the form of a convolution of g naughts sandwiched between f bar a. So convolution integrates over our variable, in this case beta. I have g naught shifted through that convolution. I have f bar a operator, and I have another factor of the Laplace transform of g naught, beta prime h naught. So look at the form here. I have exponentials of numbers times a Hamiltonian on either side of the operator operator A. I can identify this quantity as the operator propagated in imaginary time. So in the Heisenberg representation, I can say that A operator at minus I tau is defined as e to the beta prime h naught, a e to the minus beta prime h naught. Putting this all together, so we had our original equation for how A changes in time here. I've now expanded the piece in yellow to first order in F. So let's go ahead and just see if we can take all of this. So substituting the Boltzmann operator here as a Boltzmann operator in the reference and this convolution, all of those are going to be under an averaging operation e to the beta h naught, e to the beta h naught, quantum expectation, and normalized. I will get to first order A in the reference. Let's work on the numerator first. I have a F bar over, let's introduce tau as beta h bar. So I can write this as an integral over this imaginary time, d tau. And now I'll have one operator A evaluated in imaginary time. One operator A from the green term evaluated in real time. That's all of the numerator. The denominator to first order in F has everything but the average of A evaluated in real time. So it is just average of A evaluated in imaginary time. So it's not quite valid to first order in F. If I expand the denominator, 1 plus a small number, 1 over 1 plus a small number is 1 minus a small number. I find that A of t to first order in F is what it would have been before, plus something that goes linearly in F, lies under an integral over imaginary time, and is a quantum time correlation function with an operator's fluctuation in imaginary time and how that is correlated with that operator a real time later. Whew, that's a mouthful, right? But that's exciting enough. We've worked all the way through it to highlight it, throw up our hands in celebration, and now let's try to unpack it. So this is the generalization of the fluctuation dissipation theorem quantum mechanically. It looks not so dissimilar from the classical results. We have the change in A from its initial value given by a time correlation function. We have a piece that change is linear, as we'd expect from linear response in the perturbation. The striking difference, however, is this integral over imaginary time that's popped up. So what is the interpretation of this? Well, note that that imaginary time is what we're being integrated over here. Previously in our classical result, that would have just been the origin of time. What this is saying is that quantum mechanically, the uncertainty that exists because of a quantum state tells us that we actually don't ever know precisely what the origin of time is. In fact, there is some delocalization in time of the state of the system. And this tau is representing that uncertainty. We have to integrate over an imaginary path whose circumference is beta h bar in size. So there is a thermal uncertainty in where the system starts that we have to integrate over and correlate all of those quantum initial conditions with the action of A at time t later. So this integral over imaginary time represents our uncertainty in the initial condition. Note, if h bar is 0 or temperature is infinity, that contour, that integral, that cyclic integral over our imaginary time path collapses to a point. It has 0 measure, in which case that would be a classical limit. We would be looking at a well-defined initial condition. Okay, hopefully that makes some sense. There are many other ways to write this down. One can actually write it down without this integral over imaginary time. And what you would find, and what you'll be asked to do in a homework set sometime later, is to show that an alternative way of writing down this correlation function is to note that it is equal to a correlation function of a commutator of A at 0 and A at t. So the non-commutivity of an operator at one time with itself at a different time, also reflecting quantum uncertainty, is just compactly expressed in this integral over imaginary time, but is not the only way to represent it. Okay, so that's all for quantum correlation functions. Now let's actually do a application of our response theory to absorption. And we'll do this classically. Okay, so linear response, we know how a system responds to a disturbance reflects the intrinsic dynamics of that system in the absence of a perturbation. That tells us that if we can design measurements which probe the response of the system, we can invert those measurements to gain access to molecular dynamics, to molecular time correlation functions. Indeed, this is the whole industry of linear spectroscopy, encoding microscopic dynamical information. And provided the perturbations are small, those dynamics are reflecting intrinsic dynamics, not perturbed dynamics. So let's ask a simple, very mechanical kind of question associated with this perturbation, which is to ask, if I apply some time-dependent force, just how much energy is adsorbed into the system? So let's take the form of a perturbation as we have before, minus f of t times a. The absorption, the amount of energy transferred from that perturbation on average, so average over time, is just going to be the integral of that part of the Hamiltonian over time. So let's define a time average like so. And the energy, the rate of change of the energy is going to be minus f dot t times a of t. On average. So that's how much energy is absorbed. The rate of change of the energy is f dot times a. Averaged, a is the only fluctuating quantity, so it's just what gets averaged. And I could look at that over time and then ask per time by integrating from 0 to some observation time, capital T. Alternatively, I can move that time derivative off of f and onto a by integrating by parts. Like so. So those are equivalent expressions. Let's consider a so-called monochromatic force being applied to the system. Just meaning that it has one characteristic frequency. So it'll have some magnitude f bar and frequency omega. If this is a cosine function, which we're free to choose up to a phase that would be the same as a sine function, I could write this in its complex exponential form. Like so. Now, to understand how much energy is transferred, I need to know how A changes in time. F is something prescribed, in this case monochromatically. A bar of t after that perturbation is something we need to work out, but that's what linear response tells us it will be. So let's define delta A bar of t as the difference of A bar of t with its thermal average. And from linear response, we know that that's going to go like the perturbation, in this case, f bar over t, and a convolution between our response function and that force, in this case, given by the sum of complex exponentials. Now let's do a change of variables. Give me some more space. Let tau be equal to t minus t prime, in which case we can now rewrite delta A of t, f bar over 2, integral over all time d tau, chi of tau, and now tau t is tau plus t prime. Sorry, these should be primes. T prime is t less tau. So I'll have a minus omega tau and an e to the I omega t plus an e to the I omega tau, e to the minus I omega t. Associating an integral over tau, e to the I omega tau, and a function of tau, that just gives me the Fourier transform of that correlation function. I have that both for the forward Fourier transform and its complex conjugate, I omega tau. So let's define the quantity chi hat of omega times the remaining I omega t plus the difference between I omega tau and minus I omega tau is a complex conjugation. So I can define chi complex conjugate omega e I omega t like so. In general, chi omega complex conjugated, following exactly from the fact that classically chi is strictly real. So the only imaginary components enter in through the complex exponential in the Fourier transform, and it enters in linearly in omega. So the complex conjugate of the Fourier transform of chi is equal to the non-complex conjugate chi at minus omega. So we have found thus far that the absorption is going to go like this sum of chi's Fourier transforms. Let's further decompose chi of omega into its real and imaginary parts. Where chi prime and chi double prime are pure real numbers. Substituting these back in here, we have a sum of chi of omega and its complex conjugate. We can write delta A of t averaged as being proportional to f bar times chi prime of omega cosine of omega plus chi double prime of omega sine omega t. Following from introducing both this excuse me, and its complex conjugate. So now note that we have A of t being given by a sum of two terms, one that is in phase with the response, the cosine term, and one that is out of phase, the sign being odd under inversion of omega, while cosine being even. Before we go ahead and simplify things, let's note a couple properties of the real and imaginary parts of chi, or its Fourier transform. So note that the real part of chi of omega is by construction equal to the complex conjugate of its real part, which through the definition of the Fourier transform is then equal to the real part at minus omega. So it is an even function of omega. The real part is strictly even. It being multiplied then by cosine are two even products. Analogously, one can show that the imaginary part of chi is odd. In the time domain, these symmetries can be deduced by taking the inverse Fourier transform of the real and imaginary parts. So the real part, the inverse Fourier transform, would be defined as this, which through its symmetry is equal to that. And if that is true, then it must also follow that this is true, namely the sign in the complex conjugate, in the complex exponential, can flip. Which thus means that chi prime of t is equal to chi prime of minus t. So the frequency dependent symmetry manifests as a even function of time in the real time axis. So chi, the real part of chi, is even in time. Analogously, the imaginary part, the imaginary component of chi is odd in time as it is odd in frequency. Further, from causality, for t less than 0, chi of t must be equal to 0, or chi prime of t plus I chi double prime of t must be equal to 0, or for times less than 0, chi prime of t is equal to minus I chi double prime of t. For t greater than 0, chi prime of t is equal to chi double prime of t, which thus are both 1/2 of chi of t. So this tells you that a classical time correlation function contains a lot of redundant information, that in past times, the real and imaginary parts are opposite to each other. And in the forward time after a perturbation, they're equal to each other. These relationships are known as the Kramers-Kronig relations. Okay, but back to our expression for the absorption. So inserting now our equation for A of t, note that the thermal average of A is not time dependent, so its derivative will be 0, so I don't have to insert, I don't have to worry about it. So the absorption integral over this observation time, F bar cos omega t, that was the perturbation, and a time derivative of now A bar goes like F bar chi real part omega cos omega t plus the imaginary part sine omega t taking that derivative, the absorption is proportional to F squared. I have a convolution of cosine omega t with minus omega chi prime omega sine omega t from the derivative of cosine plus omega chi double prime omega cosine omega t yielding two terms, both proportional to omega, but one in which I am now in phase with cosine. We'll go like cosine squared integrated over time. That's a strictly positive number, which will build up over time. And a piece that is out of phase, oscillating about 0, which for each period will have an integral of 0. Further, the integral from 0 to infinity of cosine squared is just a half. It goes between 0 and 1 with equal likelihood. So for long times, as long as we average over many periods, the absorption, which depends on the frequency I put in, is linearly proportional to the frequency. goes like the strength of the perturbation squared and now picks up only the imaginary part of the response function. So absorption teases out or is directly connected to, if I measure how energy is transferred to a system through an absorption experiment by asking how much energy is dumped in from a perturbation. If that perturbation is monochromatic, I can read out directly the imaginary part of the response function. And through those Kramers-Kronig relationships, we should have access to the full response function. From our fluctuation dissipation theorem, we have that chi of t is minus beta, a step function, d dt of c of t, where we've introduced a shorthand for that autocorrelation function with a. Now chi hat of omega is the Fourier transform of chi of t. Plugging that in, I have minus beta, an integral over all times dt, the step function, and the time derivative of c of t. That step function kills the bottom half of that integral. Now, noting that the imaginary parts of chi of t, if I expand this out, this is cosine omega t plus I sine omega t. The imaginary part of the response function is minus beta, integral from 0 to infinity dt, the time derivative of c of t times sine omega t, which is equal to, through an integration by parts, beta omega squared, integral from 0 to infinity c of t cosine omega t, or that the absorption is equal to 1/2 beta omega squared f bar squared, and the cosine transform of the time correlation functions of A. Isn't that cool? So we found that there is a direct relationship between how a system absorbs energy, and what its intrinsic time correlation functions are in the absence of any perturbation. So from a measurement, an absorption measurement, we can gain access directly to time correlations, and thus a measure of the dynamics of a system. Further, where a system is able to absorb energy, it must be commensurate with a natural frequency of its fluctuations. The absorption tells us directly those frequencies as encoded by the time correlation function, which if I push on that system in that with that characteristic frequency, I will be able to take in, the system will be able to take in that energy. If the system does not fluctuate, it cannot absorb energy. If it does so with all characteristic timescales, it can absorb on all characteristic timescales. But if there's only single frequencies represented in the correlation function of A, imagine A is perfectly periodic, well, then I will only absorb at a single point, just whatever that characteristic frequency is of that harmonic motion. One last thing to note is that this whole quantity is even in omega. I have omega squared and I have cosine of omega of t. So absorption the form of the absorption being how much energy is transferred from the perturbation into the system, is independent of the sign of omega. Now we know quantum mechanically that h bar omega is an energy. So indeed, this expression tells you that we would have predicted the same functional form were we to consider rather than absorption of energy, but emission of energy. So classically, the evenness of this expression means that the prediction for absorption is equal to that of emission of energy, which you all should have a real problem with. It should be a lot easier to absorb energy than to emit energy, where that ratio should be exactly equal to or reflect the likelihood of being in a state for which I can emit energy. Namely, only excited states should be able to reduce their energies and emit or give off energy upon relaxation. Any system should be able to absorb and thus become excited. This actually is a real failing of classical mechanics. Classical mechanics, therefore, does not obey a principle of detailed balance in that there should be a well-defined ratio of the probability of absorbing to the probability of emitting that is equal to a Boltzmann factor. You will see as you work through this that quantum mechanically this is rectified. Spontaneous emission, rather than absorption, is exponentially suppressed by the probability of being in those excited states. That is to say that absorption could be viewed as the rate of increasing energy, emission, the rate of losing energy. Those should be balanced such that the steady state is Boltzmann. The energy in the system is Boltzmann distributed. Classical mechanics just fails. This is incorrect. So a proper theory of absorption, or really a proper theory of spontaneous emission, requires a quantum mechanical treatment. And this was observed early on in the studies of quantum mechanics, that spontaneous emission is fundamentally quantum mechanical. Okay, well, that's all I've got for today. So just to kind of step back, we've generalized our response theory to the quantum realm, introducing again our old friends, imaginary time integrals. We've discussed a little bit about time correlation functions generally, and then applied our classical theory to an absorption experiment, how we could measure time correlation functions experimentally. Our next goal is to, having now specified that time correlation functions are important for predicting response, to try to come up with models to predict the forms of time correlation functions. So much like we used Gaussian field theories to predict spatial correlation functions, we'll now use Gaussian theories to predict time correlation functions. And so next lecture, we will begin a discussion of the Langevin equation and its limits. Okay, so that's all I've got. You all have a good rest of your week, and I'll look forward to seeing you in the small groups.